Okay, so far we've made this case that in what we're interested in, we'd like to talk about the motion of fluids in the subsurface. And the most difficult suite of problems we can think of are these non-aqueous fluids, which flow into the subsurface within relatively short time periods, maybe of the order of weeks to months. They flow and they reach some equilibrium location. And that equilibrium location is really controlled by what we now know as something mainly controlled by this battle between the weight of the fluid, gravitational forces acting on the fluid, pushing it downwards, and meniscus, interfacial tension and interfacial forces holding it upwards, which kind of says something about what this final distribution of the residual fluids might be in the subsurface. Below the water table in this particular case for these denser than water fluids. And we've talked about some of the controls. And the main controls that we've said are really due to the fact that if you have a very small capillary or pore throats within the porous media, then the surface area which gives rise to surface tension which holds it up is relatively large compared to the weight of that very thin component that pulls it down. And so the resistance to it going downwards is much larger in the case of small capillary diameters. And so that really is what controls its initial motion. It's the reason why in these systems we get puddles, if you like, of fluid sitting on top of these high entry pressure lenses, which have small pore throat diameters. If we don't have enough fluid in the first place, that it kind of runs out as it goes downhill vertically in the system, then we end up not going all the way down to this lowermost capillary barrier. And so depending on these circumstances, it dictates exactly what the architecture of the fluid in the subsurface looks like in terms of the low saturation of the non-waiting phase fluid and the high saturation zones. And that's something we'd like to know maybe if we want to pull it out of the ground in remediation. What we've said is that we don't really care very much about how quickly it goes down. And so certainly if it takes a week or 2 weeks or a couple of months to get down here, that's significant maybe, but not on the lifetime of the longevity of these fluids in the subsurface, which might be for decades or not yet, because they haven't been around that long, but ultimately for centuries, because they don't degrade very, very quickly. And so we haven't cared very much about the rate at which they've moved down. We've said something about what are the barriers to it moving down. We know capillary barriers are the main mechanism by which they stop, but we haven't said how quickly they'll move down. We might be interested to say something about how quickly they move down for a couple of reasons. One, just for the academic reason of saying, you know, if we have a portion of our aquifer, this case in the groundwater zone, just academic interest, how long would it take to be there? But a much more striking interest for us maybe is that once it ends up in this stable location, and if we do have water traveling from left to right in this particular case, it'll dissolve this in relatively slow minor concentrations and take it downstream as a plume. And so to be able to say how quickly it will move downstream in a plume and at what mass loading to this compliance point downstream, we need to know something about the rates at which fluids will flow through the system. So we might want to know something about the rates at which fluid gets in place for two reasons. One, to see how quickly it ends up in this equilibrium location, and also to say something about how quickly fluids will wash through this and carry the fluids down to the compliance point. And so in reality, you know, if stuff goes into the ground and stays there, in theory, it's no real problem, right? If it's not transported anywhere. If you put a well in next door to it and it's stuck in place and it doesn't move, then it doesn't really matter because you're sucking water out of here, the water around it is pristine and you wouldn't have to worry about it. So transport is the real mechanism that we have to worry about. So the next topic that we'll talk about is really to say something about transport processes. And so in line with our idea of working with the most difficult systems, we're working not in single-phase flow, but in multi-phase flow. And so we'll spend some time really talking about that behavior. All right, so that's where we're going. You've all seen Darcy's Law. So look, let's talk about it in the broadest possible brush that we can. This is the idea of what we might be interested in. So we've seen from the architecture of these previous figures that we have a water table. We have this chimney that goes down, these lenses that occur, that are present within the system. And in these individual zones, we could think of the fact that on average, we contain components of both fluids, the non-wetting fluid and the wetting fluid. And so in reality, capillary pressures are holding these fluids in place like they did before. The architecture of these is quite irregular, as we saw from these kind of figures from before, that they're all over the place. Some of the portions are in really high saturation, so this would be a saturation almost of 100% of the non-wetting fluid and 0% of the water. In this zone here, this would be 100% water saturated and 0% of the non-wetting fluid. This smeared zone might be 30% of the non-wetting fluid and 70% of the water. And so they have some different architectures, characteristics. And so one way to think about this is to look at the real architecture, which is shown here, with a wetting fluid which is red and a non-wetting fluid which is green. And this might be what it really looks like. We know that initially in getting into this architecture in the subsurface, it's capillary pressures that are controlling exactly what it looks like and that control the distribution of it. But the important thing for us to realize that once it's entered into that kind of final configuration, then you could imagine that if you apply a pressure gradient from the upstream to the downstream, I'm getting smart about how to do this, where this is a change in pressure over a length, or if we want to call it, it could be dx, I guess, right? We will use that in this direction. Then this is the same pressure that drives the flow. And so certainly in 452, I would think that you've been introduced to Darcy's Law. And you will recall that Darcy's Law, if we did it in this same geometry, really just allows us to say something like a volumetric flow rate that comes out of the system as a function of a change in head with length. And Darcy's Law, if you write it down, is just something like the volumetric flow rate is equal to a cross-sectional area of flow multiplied through by a hydraulic conductivity times a change in head divided by a length over which that occurs. And so the units are units of volume per time, units of area, units of velocity, and these are both units of length. So ratios of two lengths have no units. And so if you work out exactly what those should be, then a length over time multiplied by meters squared is meters cubed per second, and so of course the units balance. But that's typically for a single fluid. And so what we have now is that we no longer have a single fluid, but we have two fluids present. And so the point we have to make is that what we could do is we could take this distribution of the wetting fluid and the non-wetting fluid, and if we thought about it, we could kind of centrifuge it down so that they were separated from each other. And in this idealized way, we could look at the flow within the green fluid, or the green fluid that saturates a portion of the sample, and the red fluid that saturates the other portion of the sample. and look at those in isolation. And so that's what we'll kind of do. We'll look at them in isolation. And so what's useful to know is that we can do this so long as the boundaries between the red and the green fluid aren't changing, so long as the saturations aren't changing and this other fluid isn't invading the locations that were originally occupied by that first fluid. So that's the basic requirement for that. And so you could imagine that the ability to move fluids from the upstream on the left to the downstream on the right is conditioned by exactly a little bit about what this architecture is. And so you could imagine that if this was originally sticking with this, the non-wetting fluid as being the green one, if you applied a gradient from the upstream to the downstream, either as a head over a length or a pressure, doesn't really matter, then you can imagine that if you applied a gradient across this, all that you'd get coming out of this downstream portion would be the red fluid in this current configuration, right? If you just applied a pressure gradient across there. But if you enter or introduce on the left-hand side a non-wetting fluid, the green fluid, then you could imagine that what would happen is that the saturation would change, and that at some stage you'd have this connection from the upstream to the downstream being completely across the sample. And so in the first case, you're only producing red fluid in the system as you apply gradient. Once you've enlarged this little island so that it stretches from one side to the other, then you could imagine that you could produce both the green fluid and the red fluid out of it. And if you keep on introducing only this non-wetting green fluid to the left-hand side, at some stage you would start reducing the amount of the volume which is filled with, saturated with the red fluid, and you'd only get green fluid produced. And so that's kind of the mechanics, if you like, of what we want to attempt to deal with. So the important thing is that what we've talked about for the first couple of weeks is we've looked at changes in this saturation, and those are driven by capillary forces which resist that. Once we reach some kind of stable saturation, then we can use our ideas of what we've talked about to take a snapshot at a saturation which is what? This, if the wetting fluid is the red, then this is the wetting fluid saturation is probably 90%. And in this case, the non-wetting fluid might be 90%. And so we know that when we add the wetting fluid to that, this has to be 10%, etc., because we know that these two, when we add them together, have to sum to 100. So what we'd like to be able to do is be able to say something about the rates at which we can move fluids through here. And for a couple of different reasons. And maybe at the end of the class we'll get through to assignment number 4, which kind of uses this concept. So for instance, in this particular case, if the wetting fluid is water, which is the red fluid in this case, and this was a little lens of this DNAPL, you can imagine that the velocity, the flow rate of water through this would be determined by the average permeability of this system. So that's what we'd like to be able to do. So we'd like to be able to figure out exactly what this flow rate is, because if we wanted to know, for instance, the mass rate of DNAPL that comes through here, it's going to be equal to the volumetric flow rate, Q, multiplied through by the concentration. And this would be this would be the solubility, which is a concentration. But if this is the solubility in terms of grams per cubic meter of water, for instance, grams of DNAPL per cubic meter of water, then what this would give would be the mass loading. And this would be the mass loading that's carried downstream. So that's the basic reason why we might want to do it. So what we're interested in doing is saying something about figuring out the magnitudes of permeabilities. Okay, so that's where we're going. Yeah.
That L represents the L in
Length. It represents the L in Darcy's law, which would be the length across this sample here. Yeah, good question. Okay, so we could go straight to this and go through this, but let's just do this by me scribbling, if you're okay with that. I think I'd prefer to do that, and I think it's going to work out better for us. So there are two things that we'd like to figure out. One is what Darcy's law is, which you know for single-phase flow, But when we deal with two phases, we have to think in terms of the relative permeabilities. What is the relative permeability of this medium to water, and what is the relative permeability of it to the napple? And those are the two questions. So let me look for some space here. So the geometry that we will think about is exactly this geometry we talked about before, which is a sample. We'll choose a datum, which is this. We'll have water flowing out of here at some volumetric flow rate. We'll have a tube that comes out of here that has a water level in it. We'll have a tube that's upstream that has a different water level in it. And maybe we'll draw a couple of different geometries on it. This is an upstream elevation and an upstream pressure head. And conversely, a downstream elevation and a downstream pressure head. The same pressures you'd feel in a swimming pool at these two locations. We will use, so you'll realize that Bernoulli's law, right? Elevation head, pressure head, velocity head. We throw the velocity head away because it's not significant. And so we write the total head here as the sum of the elevation head plus the pressure head plus the velocity head. And we put this to 0 because it's tiny compared to the other ones. And what we can do is we can then write Darcy's law in terms of this as volumetric flow rate, which is equal to the velocity multiplied by the cross-sectional area. We alluded to this before, that this is the cross-sectional area. And if I just switch that around, cross-sectional area times hydraulic conductivity, the change in head over a change in length. And if you like, this is dl. We can make the case, if we wanted to, if this was the x direction and this is the z direction, we can make the case that this might be a minus in here because the gradient of head is in the opposite direction of the actual flow velocity, which is a vectoral quantity. But nonetheless, we can define the behaviors like this. And so if you wanted to think about this, you could think about it maybe in a slightly more abstract form. If you kind of drew this little thing on here that is drawn in terms of this point here, which is this, or I guess it would be this point here, right? This point here and this point here. Is a change in head over a change in length. So I was just going to draw that here. So I've kind of already drawn on the top. Don't need to now. But just draw the same thing. So it's a change in head that occurs over a change in length. This is this. This vertical component, I suppose we think of as head, and this is length. And that's basically Darcy's law, which is the same as writing cross-sectional area, hydraulic conductivity, change in head, and let's just substitute length for x. Okay. So it's important to realize that this is what's driving flow, the head. Not just the pressure differential, but also the elevation difference that's in the system. So what we could do, I suppose, is if we wanted to write Darcy's law in terms of a velocity, then we can do that, which is just this. So we haven't done anything, we just divided both sides through by velocity in these cases, and we end up with this term here, basically this term here. And what we could do is we could realize that the gradient has two parts to it. It has this hydraulic conductivity, K, but it's multiplied by a change in elevation with X and a change in pressure divided by unit weight divided by X. So these two gradients add to each other. And I suppose if you wanted to kind of draw them on here, they would be kind of, this would be dz dx in green, if you can see that. And the difference in pressure would be this term here, which is really change in pressure with X. And so all we're doing is we're realizing that, well, it's probably easy to write it out, that head is equal to elevation plus P over unit weight. So in other words, substitute this into here, realize that these are both over the same base length, and you end up with this expression. That's all I'm doing. So maybe don't complicate things by doing anything. So, and there is a reason for doing this, ultimately, as we'll see. So what else can we do? We also realized that first time we met actually in person, was that we made this distinction between hydraulic conductivity, density of the fluid, and gravity being equal to permeability and viscosity, just by definition. Units of this are hydraulic conductivity, which are units of length over time, velocity. Units of this are permeability, which are meters squared. They don't change for the material that you're talking about, whereas this would change for the material if you flow different fluids through it. So what we could do is we could rearrange this and substitute in this. So in other words, if I just rearrange this to give hydraulic conductivity is equal to density, gravity, permeability over viscosity, just by rearranging this. And if I throw this into here, then we have Darcy's law now written in terms of minus K over mu, rho g, and the same terms that we had before. dz dx, which might seem a bit esoteric, plus the change in pressure with location, and this unit weight term, which is just 1 over rho g. So if we look at this term here, then I guess ultimately what we could rearrange this into its final form, and that would be the velocity in Darcy's law is just equal to permeability divided by viscosity. I'm going to take this term inside here, change in dz dx, rho g, plus change in pressure with X, and I've got rid of this. So in other words, basically I've just taken this inside here and then got rid of it from the outside. So this is an important relationship, and it may seem kind of a hammer to crack a nut, but it's quite important for us to be able to define this, because it says something about what happens in our system. So what does this physically mean? So we could take two different cases, one of which is very straightforward. Say we took a Darcy test, an experiment, where we have a water table difference on both sides, where this is, what is this? P1 minus P2 over unit weight, which is driving flow. And so this would be this magnitude driving flow. We know that flow would occur in this direction, and it would be some magnitude v. We know that our coordinate system is x horizontally and z vertically. And so if you look at this expression here, what is this ratio of dz dx? X is in this direction, z is orthogonal to it, so there is no component of z in the x direction. And so by definition, this term has to be equal to 0. And so if we write Darcy's law, then the velocity is just equal to permeability, viscosity, and the pressure gradient arranged over that sample. Probably the way that you think about Darcy's law, if you think about it. Not perhaps something you think about every night necessarily. But this is saying that this pressure gradient is exactly what drives the flow. And so why do we care about this whole thing here? If we draw this slightly differently, and if you draw this, maybe think of it as being in a swimming pool. And if we draw it so that this sample is vertically upwards, this now is the direction of flow, which we'll call in the x direction, and it has some velocity v. This is the z direction. And if we now look at these components, this term here is exactly aligned in the direction of the z-axis. They're collinear. And so by definition, this has to be either plus or minus 1. It has to be 1. It could be plus or minus, depending on how you draw your coordinates. I guess in this way, it's minus 1. So the importance of defining that is that this is the velocity of flow. So this term now becomes 1. And if we write out this term for the velocity, what would you expect it to be? So if you take a core and it's got fluid in it, and you take that core and you put it in a swimming pool, what do you expect the flow rate to be as it comes out of the top or the bottom of that core? The water was happy sitting in the swimming pool before, it wasn't moving. And so when you put a core in and saturate it, it probably shouldn't be flowing either because it's static fluid. And so the mere fact that this comes out to be this term here, and I'll write the individual terms, dz over dx, rho g plus dp over dx. This term here is equal to minus 1. What do we have? P is equal to h gamma. And so we could substitute this into here. And this term would be equal to dp dx. Substitute this as h gamma. So this term dh dx times unit weight is exactly the same as this dh dx term here. They exactly subtract from each other. And so the idea is that this term here has to be added to be able to make sense of this, because if you have a static fluid, then it has a gradient that's just due to its self-weight, which is going to be equal to this, right, as you go down. P is equal to gamma z, minus actually, I suppose, right? And the fact that pressure is increasing as you go down here is no indication that flow is going to occur because it's just sitting at self-weight. And so it's a long-winded way of saying it, but the reason that Darcy's law looks like this boxed equation here is because of this term here, which represents the self-weight of the fluid. And you avoid that term if you're looking horizontally, you just don't have to worry about it at all. But if the fluid, the control volume is inclined in any way, then all of a sudden that makes some difference. Okay? And so, maybe in closing, it would be worthwhile saying that the velocity is always equal to the hydraulic conductivity times dH dx. Oops. You could always, if you wanted to, write this as head being equal to pressure over unit weight, in which case you could make this expression look like hydraulic conductivity multiplied by pressure dx. This is jumping around, I guess because I'm holding it wrong. You can always write it as that, so long as you're mindful of where things are going. And if you wanted to, you can always substitute this value of hydraulic conductivity for the magnitude of permeability divided by viscosity multiplied by unit weight and gravity. And so you can always make these substitutions. And so the important thing is to realize that this kind of messy term that represents the self-weight of the fluid merely explains the fact that if you look at the pressure distribution in a static fluid, it increases as it goes down, but it's not this pressure distribution that drives flow, because there's a unit weight. This is due only to the unit weight of the fluid in a static fluid as you get deeper in the fluid. And so you need to account for that. And so the utility of doing that is that, actually it's probably worthwhile doing this actually. So let me try this. What would be, if you took a swimming pool and if you drew the trace of pressure versus depth? We've already made the case in a static fluid, the trace would look like this, which merely comes from this expression which you know well. Right? If you look at the value of the magnitude of head, then the magnitude of head would look exactly like this. It would not vary in depth. And we know that, right? Because if you take a portion here, then the head comprises a portion which is the elevation of that point relative to a datum, and a part which is the pressure divided by the unit weight. And if you move this little dot up or down, these proportions change, but they always sum up to the same value. And so I guess actually it would only be 0 if you took the value here, the datum here as being 0. So if you took the value here as z equals 0, then the value of head would be 0 here. If you took the datum at this point, then the value of head would be this height h. And then the magnitude of this head as you go down in this fluid would actually be this height here, which is h. So I don't know if that's been very clear actually now that I look at it. But the point is, you cannot necessarily neglect this outright without thinking about exactly what it is. And so what we'll tend to do is to try and calculate things in terms of horizontal flow, which becomes much simpler. This truly is the case for Darcy's law. If you have horizontal flow, you don't have to worry about this extra term. But if you are looking at non-horizontal flows, then you have to incorporate the true value of this body force term. So maybe we'll summarize that at the end. So that's one of the issues we have to deal with. What is this difference between head, and what is this difference between pressure, and how do they relate to each other? And so that's the first part, hopefully, that we understand a little bit about. The second part is to figure out exactly how we might define these behaviors for multi-phase flow. And I want to go to this to be able to make that case. Okay. So we said before that if we look at multi-phase permeabilities, multiphase flow. And so we need what we refer to as relative permeabilities. So the idea is this. We said before that we could take, so let's work on this idea that we have a core, and indeed our core is horizontal. So we don't have to worry about all of these nuances that we just talked about. And we're going to take this core and we're going to saturate part of it with a wetting fluid, water, part of it with a non-wetting fluid. We have, as we could imagine, two areas at the end. And so the overall area is equal to the sum of those by definition. And we're going to do exactly the same as we did before in terms of making sure that we have a fluid going through here from, in this case, left to right. And it has some pressure, and it occurs over some length. So what we could do is we could calculate for, let's call this fluid 2, and let's call this fluid 1, with these respective areas. If you want, we can do something with the colors. And so if we wanted to figure out exactly what the volumetric flow rate was of fluid 1, then we could write this as the cross-sectional area A1. We could multiply it by the permeability of part of the core 1, and I guess this is kind of split longitudinally along the length here. Viscosity of fluid 1, the change in pressure as we go along the sample of fluid 1 over the length of the sample. And so that's Darcy's law that we've written. This would be the cross-sectional area 1, and we have that defined as a magnitude of flow. If we took this and we multiplied both sides by the total area of the core, because if we are gathering fluid in a bucket out of the bottom end of this, some green fluid comes out, some red fluid comes out, and it's the total area that we would be able to measure because we don't necessarily know what proportions these are. And we have this then written as, I'm just going to rearrange this, change in pressure over length. Well, I should have put this here. And let's think about the terms that we use. We said that fluid 1 is going through here. It's going through the area of the core which is saturated with fluid 1, which is A1. It has the fluid pressure difference between upstream and downstream of fluid pressure 1. And we could put 1 on here, but we don't need to, because we said that the permeability of a sample doesn't matter if it's oil going through there, or air going through there, or water going through there. It's a fundamental property of the porous medium and doesn't care about the fluid. And so this stays to be just not labeled. And so if we want to calculate what the volumetric flow rate through here is, it's the overall area of the sample, it's the permeability of the medium divided by the viscosity of fluid 1, it's the ratio of A1 to A, and it's the pressure gradient, which we could call, if we wanted to, X. So this is kind of important because this term here that we have, if you think, it's really a proxy for the saturation. If you think about all the pore space in here being the same size pores, then if the red cross-sectional area is 0, the saturation of red fluid is 0. If the red area is 100%, then the saturation is 1. And so A1 over A is approximately equal to saturation 1. So we could think of this being saturation S1, roughly. If we do exactly the same for the other fluid, then we have Q2 is equal to, again, the cross-sectional area, the permeability divided by the viscosity of the fluid, not 1, 2 I guess, multiplied by saturation 2, and the pressure change over length of fluid 2 and fluid 1. But actually, the change in pressure 1 and the change in pressure 2 are roughly the same. So what this gives us is the ability to be able to figure out exactly what the flow rates are of each of these fluids. And so what we would see is that we'd like to be able to write this overall equation just as the flow rate of one particular fluid is equal to the cross-sectional area times the permeability of the core, the viscosity of the fluid, multiplied by something which we'll call a relative permeability of fluid I, and the pressure gradient. And the reason we like to do that is because this is basically Darcy's law. This is the same as A K over mu dP dx, but with some extra term in it, which is a scaling parameter. Yep.
What's the whole point of having A the same, like two of A the same time? They're gonna cancel each other.
This one here? No, well, they do cancel each other out. We've just put them in because we've added them that way. The reason for doing that is that always when you do an experiment, it's easy for you to know exactly what this cross-sectional area is of the whole core because you physically have in your hand. But you have to look inside it to be able to see what the saturations are. And so you don't necessarily know that. And so hang on 2 seconds and all will be revealed. Go ahead. Okay. Sure? Okay. Right. So the reason for doing this is you could imagine that now we could draw a figure, and it would look a bit like our relative permeability versus saturation curves. I'm just trying to make sure that I fit it on here. I found out how to draw straight lines on this, I guess. New technology. And so what we could do is we could write relative to the saturation of water, which we know goes between 0 and 1, or the saturation of the non-wetting fluid, which goes between 0 and 1, just as we did for capillary pressure curves before. And we know that this term here is going to be for fluid 1, which is our, this is I guess our non-wetting fluid, right? Is when the area of the non-wetting fluid is equal to, so initially if the area of this non-wetting fluid is equal to 0, then the flow rate through this is 0. And so I think that this is going to be this term here. So when the non-wetting fluid saturation is 0, the relative permeability, which is the ratio A1 over A, which is the same as saturation of fluid 1. So if the saturation of fluid 1 is 0, then this term here is 0. And when the saturation is 100% of this, then it's going to give a ratio which is equal to 100%. And so if you look at least for the red curve, then the curve that goes through those, this is just this. This scaling parameter here is just the saturation. If you look at the green fluid, you can do the same again, but now with respect to the saturation of water. When it's 0% water saturated, there's no green, and there would be no fluid going through it. And so if we plot the saturation of water for the green fluid, when it's equal to 0, it would equal to this 0 here. Whoops. When it's equal to 100%, it would equal to 100% here. And this line here that connects these is just the relative, this term, which is our relative permeability. So these, in a very simplistic way, it's not quite true, as we'll explore in a little while, is that this would be what? This would be the relative permeability interesting. Relative permeability, that's right, I agree with that. Relative permeability here would be the relative permeability of the wetting fluid. And we'd call this KRW. And on this term, this would be the relative permeability no surprise here, of the wetting fluid, water. Yep, now I'll take it. Yep, I'm listening. Yep.
What's the relative permeability on the chart? Is it the slope or the angle? Yeah, I'm confused what you're drawing.
Say again, sorry?
What's the relative permeability on the chart there again?
The relative permeability is this term here. It's this ratio of how much of the cross-section is filled with a particular fluid, and it is a in direct proportion to the saturation of that fluid. And so that's why it's really a saturation versus a saturation, and that's why it's a straight line and goes through those two ordinates, 1, 1, 1, 0, 1 at the top. Yes?
How can the non-wetting fluid will have an area of 0?
A different. So we can only be in the core. Okay, well, let's draw the core as we go through here. So the core at these different locations can be at a given saturation. So if we drew the core at this particular saturation here, it would be at a saturation of water which is 0. So let's get our colors right. Water is green. And non-wetting is red. Is that right? Yes. Okay. So in this particular case here, the saturation of water is 0, and therefore the whole cross-section of this would be the non-wetting fluid. At this stage, we're the exact opposite. The saturation of water is 1. And this is only the wetting fluid. And right in the middle, if I draw it in a neutral color for here, it is going to be half of one and half of the other. And so clearly a core can only be in one state at one time. Either it's 100% saturated with the DNAPL, or 100% saturated with water, or some magnet in between, but it can only ever be on one of these vertical lines that goes through here. And so really all we worry about is the fact that there's a relative permeability of the, in this case, the wetting fluid, and a relative permeability of the non-wetting fluid. And so if you think about these, this would be how am I going to draw that? I can't draw it that way. What would it be? Yeah, these have to be the relative permeabilities of the system. And I guess what it has to be is that this would be the relative permeability of the non-wetting fluid. And this would be the relative permeability of the wetting fluid. And I think the other thing you'd see is that if you add this height here to this height here, you end up with 1. They have to add to 1. It's not true, but take it on this. So I don't know if this is obfuscating things or making them clearer, but the basic idea is that we have a core, we can measure the cross-sectional area of the end of it quite easily. Physically, we can hold it in our hands and do that. But the rate at which we can push fluids through it is not very convenient for us to be able to look at the end of the core and see what portions of the end of the core are saturated with wetting fluid and non-wetting fluid. If we could do that, then we could immediately say what the overall permeabilities of that core were, but we can't do that very easily. We can quite easily measure the saturation by doing certain things like taking a sample and boiling off the water, or boiling off the DNAPL first at a lower temperature and then boiling off the water at a higher temperature and get the different saturations. So we think we can get the saturations of the fluids, and if we have the saturations of the fluids, we have the ability to calculate what the flow rate through our system is. I'm going to make it smaller so it all fits on. So to see the big picture, all we've done is we've said that we can use this cross-sectional area of these two fluids as some measure of this relative permeability feature that we've decided. Right? All right, let's go and look at some figures instead of the analysis. Okay, so we don't need to do this. But this is a key figure here, I think. And so let's spend a bit of time talking about what the components of this figure should mean. Okay. So I took a few liberties, but if you remember exactly the curve that we had was something that looked like, I'll draw it over here. Actually, I can make it even bigger. Is that we said that this curve actually looks like, oh, and we said that the curve actually looks like this. Let me use, didn't mean to do that. Let me use the same color scheme that we'd used before. And it's on the same figure. Saturation of the wetting fluid, 0 to 1. Saturation of the non-wetting fluid from 0 to 1. That's basically the expression that we drew before. And so these were these X curves, so-called X relative permeability curves. And this is relative permeability, which varies from 1 to 0. They're straight lines because the equation of this curve, as we wrote it before, was that the relative permeability of the wetting fluid, which is this red one, is just equal to the saturation of the wetting fluid. Similarly, the relative permeability for the non-wetting fluid was just equal to the saturation of the non-wetting fluid. I guess that's stating it quite straightforwardly, right? This relative area that flow occurs through is the relative permeability. That's all it is, nothing more than that. If we draw these curves to represent that, then we can choose a particular saturation that we find ourselves at. And that might be this blue curve. And we could also do that on this curve. This curve on the left happens to be a real one. And it shows some slightly different features. It shows that instead of going up to this top left-hand corner, the green, it probably does, but it's not very easy to get in this region. And it also goes down to the lower ordinate here. And likewise here, this would be. And so it's not quite this curve, but the rationale of this curve is clearly due to, if I draw this out, that's what's going on. And you see this in the cameos down here, exactly the same. So physically, this curve is just saying that the scaling of the amounts of these different fluids that can go through here is controlled by the cross-sectional area that is filled with these different fluids. Typically, they're not filled en masse, but it's really kind of distributed so that if you look at individual pores, then the wetting fluid, which is red, is going to be this monomolecular layer that covers these grains. And the non-wetting fluid is the stuff that sits in blobs in between these grains. So it's not as if it's fully, certainly when it's 100% green saturated, it is 100% of the cross-section is filled. But when it's at these intermediate points, if you look in microscale, you just see green and red dots all together, covering with each other. And you wouldn't be able to pick out the fact that it was a different, I guess it was a, whatever the amalgamation between red and green together as a color is. I don't know what it is. Blue and yellow is, green is blue and yellow, right? So it doesn't matter what it is. But you can't pick that out. But what would happen is that this relative permeability would describe the amount of fluid that would come out of this. And physically what it means is that on this side of the curve, where we're at 100% of the non-wetting fluid, which is this point here, you provide a gradient across here, a pressure gradient across here. Then from what we talked about before, the only fluid that you get out of here would be the non-wetting fluid because it's continuous. The red isn't. Likewise, when we look at here, the only fluid that you get out of here is going to, by applying a pressure gradient across it, is going to be the wetting fluid, which is the red fluid, because the green fluid now is no longer continuous across here. And so we can use that to calculate the volumetric flow rates of each of these fluids. So the flow rate of fluid Q1 is going to be the total area of the core. And so if I try and be smart and draw this in perspective, so that this is the total area of the core here, then the permeability divided by the viscosity of fluid 1 multiplied by the relative permeability of fluid 1 times the pressure gradient gives us all we need. That's all you need to take out of this class, today's class. This. So if 1 is the, hopefully 1 is the red fluid. Conversely, if you want to calculate how much of the second fluid comes out, I'm going to draw this with the same area, the same permeability because they are the same, divided by the viscosity of fluid 2, the relative permeability of fluid 2, and the pressure change. I guess you could make the argument that this, yeah, let's just leave it there. So the only things that have changed are the pressures driving flow across the system are the same, but the only thing is that you have two different fluids involved. One has a viscosity of fluid 1 and one of 2, and that we're using two different relative permeabilities, which just scale the cross-sectional area of flow that goes across there. And that's it. So those two expressions on the left-hand side are physically really all you need to pull out of this. And so long as you know what the saturation is, which you hope you might know. And so in this particular case, let's say you know the saturation is this magnitude here. then you have the two relative permeabilities. So this would be KR1, which is this, which is what? It's about 0.01, not that small maybe. So this is 0.5, it's probably less than 0.5. And this would be the second one here, which is, you choose the number. That's it. And so if you wanted to know how much of this fluid was being pushed out of the system, then it would tell you exactly what that amount was. If you chose a different location maybe for where you wanted to measure these two saturations, say it was this point here, how much of the water would be flowing? Finite? Zero? No. Zero, right? Relative permeability of water is 0. Relative permeability to the other component is 1. Is not 1, but 0.9. So this would be the stat here. So the upstream and downstream of the green fluid are pinched off. Of the red fluid are pinched off. And so there's no communication between top and bottom. And all that's flowing is the green fluid, which means that this number is close to 100%. There's none of the red fluids that's flowing, and so this is indicative of that. So that's really physically all that's going on. So that's an important watershed, if you like, no pun intended, for us to be able to calculate these different flow rates. The other way that we can maybe put this into context is to draw these together in terms of something we've also seen. I'm not sure if this has the right aspect ratio, but let's go with it. And so the other thing that we've seen, which is useful to put together, is that we could take two curves that we have so far. And I'm going to draw them one above the other. Because they say something physical about our system. And they'll have the same axes. The wetting saturation on the bottom, and the non-wetting saturation on the top. The one that we've just drawn is one for relative permeabilities. Which we called K sub r. We know that it goes between 0 and 1. And the one on the top is going to be capillary pressures. Which we called capillary pressure, which is the non-wetting, difference between the non-wetting and the wetting pressures, two different fluids. We know a little bit about what these curves look like. See if I can draw it better than I usually do. We could draw some bounding curves here. That we've seen before. And we can start filling in all the terms that we knew before as well. So what is this? This is the irreducible saturation of the wetting fluid. In other words, we can't dry the sample out of water any more than this magnitude here. So as we first invade with, or imbibe, so this is drainage. This is imbibition. And as we move, I guess, did I draw that the wrong way? This is the minimum amount of water that we can remove from the system. We'll always have this amount of water in, even if we have this other remaining amount of DNAPL. The irreducible saturation of the non-wetting fluid is this one. And that these conform exactly to what we just looked at in terms of the relative permeability curves. The relative permeability curve for water would be something like this. And it didn't really go across here, but it went up, has to go up to 1. The irreducible magnitude relative permeability of the other curve looks like this. And I think on the other curve we had this other amalgamation between these two, which looked KR, which one's which for these? This is the relative permeability of the non-wetting, and this is the relative permeability of the wetting, of water, if you like. And so this is the relative permeability of the wetting plus the relative permeability of the non-wetting.
Wetting is the water?
Water, yeah. Oops. And so that kind of brings everything together in one figure that represents really probably, I guess, are we on 2.4 or 2.4 today? So it brings in 4 classes together. So this says exactly what happens in terms of the capillary pressure versus saturation curves. How if we start off here with a water-saturated core, we can push a bubble of this fluid into here and drain the water out of it, in which case we'd move up along here, up to the maximum amount of water we can remove out of it. And then if we back off the pressures, we'll start filling up, imbibing with this, with water outside it. So we push it out, then we imbibe it. The consequence of this change in saturation is what drives the transmission characteristics, if you like, of these two fluids, and describes when we're able to get the magnitudes of these of the liquids through here. In this case, we will be communicating only with this non-wetting fluid. There'll be 100% relative permeability of the non-wetting fluid and 0% relative permeability of the wetting fluid. And at this side, it'll be the exact opposite because this point has switched to this. The relevance of this, I guess, is that the ability to be able to get fluid into it, if you like, this defines the architecture of exactly what the fluids present within the system look like. And this defines the flow rates that we can get both in the water and within the non-wetting fluid that goes out. So this is flow rates. And if you like, this is architecture of the system. So maybe not such straightforward ways of looking at things, but something that we need to be able to deal with because we'd like to be able to say something about how quickly we can flow fluid through here. We don't have time to talk about it. But assignment number 4, it's a little bit down the road, relies directly on what we've talked about today to be able to say something about how the magnitudes of flow rates occur in these systems and how they're driven by the magnitudes of Darcy's Law, written to be able to represent these two-phase flow systems.